Thank you, Ruching, for all that work yesterday with this. So, my name is Geoff Perumal. I am one of the product specialists for our volume cryotomography portfolio. And today I'm going to talk about correlation and confirmation, including a fluorescent chamber or a fluorescent microscope inside of a dual beam chamber to help improve the efficiency during the cryo-electron tomography workflow. So if it's all right with you all, I'm also going to just stop my video in the interest of bandwidth so you all could see me and hopefully my movies play nicely. But I always like to just briefly start with a overview of the tomography workflow. I think it's really important to understand a few bits to it, which I'm sure this audience knows very well, which is while the physical act of electron tomography occurs in the TEM, which we're seeing off here on the right, it's a analogous procedure to that of room temperature tilted tomography. Obviously, the twist will be that it's being done under cryogenic conditions, and whereas under room temperature conditions, typically you have a section which is placed down onto a grid. We don't always have that luxury in the most optimized workflows. We tend to thin down a cell which was planted or seeded on a grid using a focused ion beam. But what I really want to stress is that, part of this workflow is a series of checks. Getting into the TEM, the cryo TEMs, are first off costly, but secondly, they tend to have quite a long queue for those of you who are using it. It's not like you do a sample prep on Monday and you acquire on a Tuesday. There's usually a long line that goes into it. So we really want to make sure that when you get onto that TEM, those resultant lamellae or the thin section from that cell is as valuable as possible to maximize that time. So whether we start out at the freeze step or go through the T or through the fib, it's really nice to do as much check and quality control prior to getting into the TEM. And that's what including fluorescence inside the fib chamber is going to offer. So just a very quick bit on the actual tomography workflow. That thin down lamella is brought into your TEM. A series of projections are acquired on a targeted ROI somewhere in the neighborhood of about 2 to 3 degrees per angle or per image. Hopefully getting up to plus and minus 70 to really minimize any missing information. Those images are aligned, and I'm sure you're probably all familiar with this slide for those of you who've seen a Thermo Fisher tomography presentation before. We're looking at a chlamydomonas, which, on the left, we're looking at the aligned lamella. On the right, we're looking at the 3D projection of it, or excuse me, the 3D segmented area of it. And we see the beautiful organelles, which is what the strength of that cryo-TEM will be. The Golgi, the beautiful ribosomes. You could even make out a nuclear pore here on the left. But here's the thing about this is this was done without any guided approach. So essentially a number of chlamydomonas were frozen down onto a grid and several lamellae were cut with the hopes of getting a beautiful image such as this. So what I'm going to do now is just take a step back in this process, and we're going to do a little math together as I play out this obvious movie here. So what we're looking at before I hit play is this is a animation or a cartoon of a cell which has been frozen onto a quantifoil grid. In comes the focused ion beam, shaving away above and below a potentially targeted area of interest. But here's the mathematics behind it. What you're looking at here is a representation of the 200 nanometer lamella from this cell. Cells can be anywhere from 3 to 5 microns in depth, meaning you're removing anywhere between 75 and 95% of the cell before you even do any examination. So that means that somewhere between 3 and 4 to 19 out of 20% of our times, you're going to miss your target if you're doing this blindly, which is why that previous chlamydomonas, there was lots of samples milled. Um, in an effort to be more efficient in the TEM and to make this resultant lamella that much more impactful, including inclusion of a fluorescent microscope in the chamber is only going to be beneficial. So off on the left here, we're looking at a cryofib. Standard geometry of a fib still holds true. You've got your electron beam firing down, your fib column, which is kind of cut off here on the left, meeting at that coincident point. But off here on the left here, hopefully you could see my mouse moving. is the integrated fluorescence system. So it's a single objective 20x 0.7 NA, which is optimized for cryotomography. This is not going to have some of those specs which you might be accustomed to from confocals, mainly due to limitations of field of view. We need to create a little bit of working distance between the sample and your objective to prevent any devitrification. But beyond that, all of the hallmarks of fluorescent microscopy would hold true. We've got our mirror in place, a vacuum seal to allow the fluorescent signal to go into the chamber, bounce back onto our source. So things like that are typical of fluorescent microscope and hold true in this system. So the idea behind this is instead of having to cut 20 lamellae and hope that 95% chance of missing, and which will leave you 1 in 20 of hitting, could be reduced so that we're more efficient in the fib. And that's the idea of targeting with fluorescence. So the workflow for this, I'll give you a couple slide overview of it, and then what I'll do is move on to a few videos where we actually do this in practice. Goes as follows. So what you're seeing in the background is a SEM image of a frozen grid. Following that SEM image, the actual grid is shuttled 180 degrees, remaining inside the chamber to the fluorescent microscope position. From here, being that we do have, and excuse me for failing to point this out before, we've got the ability to image in 4 different channels. So in this case, we're actually only using 2 of them. Blue, obviously, being DAPI for the nuclei. The green here, a mitotracker signal. We're able to assess our grid. So we have an idea of, is my fluorescent signal in place on here? Where is it located? Actually is also going to be important. We don't want to mill on grid bars, but I won't dive into that part of it. We'll stick more towards the fluorescent acquisition part of it. But from there, what we can do is identify a particular ROI. Now, this is just a generalized cell. I'll show you some more specific examples in a minute. And then from here, that process of ablating down to that final lamella, and then going back and confirming that targeted ROI remains in the lamella is now the process. Now, what I'll say about this is a few things. I gave a kind of similar talk when one of the previous BioEM talks, but the difference here is what I presented previously was a completely automated process. And I think automation is going to be extremely valuable for this. The rationale for that would be obviously when you have an abundant fluorescent signal, you could run it through automation and feel very confident that you're going to wind up with fluorescence in that lamella. For instances where your target may be more sparse or your target might be a little bit smaller, it's probably a little bit more optimal and preferred for the user to go ahead and sit in front of your microscope and babysit it to ensure that your fluorescence remains in there as we go from 5 microns down to 200 nanometers. And that's exactly what I'm going to show here in this next series of about 5 movies. So step 1, after again we've done our SEM overview image of the grid, is to bring it back to the fluorescent microscope as we showed before. And now this is a similar base sample. In this case, we're using 2 channels again. Blue for DAPI, green is another mitotract label. These are Chinese hamster ovary cells. So now the first step in the process would be doing a little bit of assessing of your fluorescence. Maybe we found an interesting area where we're going to target an ROI for. Being that we do have an overlay here, there could be a lot of signal coming at you, so we could take off the SEM image to better assess our fluorescence. There is a piezo drive on here, so this isn't just a 2D plane. We understand that fluorescence could be anywhere throughout your cell, so to be able to go ahead and look through the cell, identify your region of interest is going to be critical, and that's exactly what's happening here. We turn back on the blue as a reference point, and now we've placed our potential ROI here. Now, what I'll ask you to do throughout these next 4 movies is just kind of remember this blue nucleus here. It's going to be up just off-site of our ROI target. But so quickly, just to recap where we are, is we've assessed our grid. There's been no milling done, so this is our full cell here. And now the process of thinning can begin. So So this quick movie here is just the actual process of going from that 5 micron bulk down to about a micron and a half, 2 microns remaining. This is the actual thinning here. These boxes depict above and below that area which we want to target against. Obviously, as I'm sure you can imagine, there's a little bit of correlated software which comes in here to allow us to quickly go between the fluorescent microscope and the SEM without having to refine our area. Oh, excuse me here. I think I just went back one. And I'm just going to move this movie to the end here to basically point out that now we've got our 1.5 micron bulk, which we want to assess because obviously as we look down from our SEM, we can't tell for sure, does that fluorescence still remain in here? So to be able to, in real time, shuttle back to the fluorescence, and now we could see that bulk right here, and I'm just going to play this movie as I talk, is going to be just so critical. So it's a plus minus approach. So plus, great. That means we can move on. Minus, if we don't see that fluorescence, maybe you move on to the next area where you've also located your area. So in a second here, we're going to zoom in on this area. And sure enough, as we play around with the histogram and decrease some of the overexposure, we could see that nucleus, which I was referencing, and off-site here, once the fluorescence dims down, we could see the targeted area. So this is that nice first check that yes, my fluorescence does remain. And now we can continue on in the process of going from bulk down to 200 nanometers. And we'll go right back to the fib. So again, all of this happens in chamber. So there's no shuttling out, potential places where contamination can build up. We're looking at this obviously through the eyes of the fib. There's no scale bar on here, but we've brought it down to about 200 nanometers, as you see. Now, the next step without a fluorescent microscope would be to simply bring it to your TEM. Hopefully, there's some correlated software which could speak between them, and we've got that nicely taken down. I think XY coordinates is pretty rudimentary at this point in the CLEM workflows. But knowing that you're at that lamella isn't the challenge. The challenge is, does it contain that fluorescence? And so the last step of returning to the fluorescent microscope again in chamber before removal is just going to be that much more critical. So here is that milled out area. Again, simple XY shuttling between the two locations will ensure quickly that you're back at the area you were milling. We're going to zoom in a second here. And what you'll see is, now bear in mind that nucleus, which we had used as our initial point of reference, it's going to be a little bit more dim, which you see off here. And that has to do with the fact that we've gone from bulk down to 200 nanometers. But nonetheless, we could see that the fluorescence still does remain here, allowing you to feel quite confident that when you get into that TEM, that your area of interest will in fact remain. So I've got here a generic wrap-up slide to basically go through these steps. We start out with bulk. We identify a fluorescing area of interest, do a bit of alignment here. Switching over to the eyes of the fib, we can start the process of thinning. We could do some confirmation of our bulk that that area does remain, going from a couple microns down to a couple hundred nanometers. Before we get out of the fib, we can go back and confirm that the fluorescence remains in there. So I guess I want to make a couple other points here about this. Again, we talked previously about how this can be done automated, and it certainly works. I'm a believer of when you have something very rare, automation is nice, but none of us really feel confident unless you're watching your process happen, which is why I wanted to go back and talk about the manual approach to this as well. And while I did previously just show a simple instance of doing a one return, or actually two returns, after bulk and after thinning, do keep in mind that our science is precious to us. And so I point that up because you have the ability to go back as many times and assess your fluorescence in this process. It doesn't have to be simply after bulk and after thinning. It's a really nice way to ensure that that lamella does contain it, limit the number of lamellae which you need to cut if you actually have it in the first place, and make more of your time back on your TEM. I believe that's my last slide here. So what I will do is stop presenting if I could find that button, and I will turn back on my camera, and I'm Certainly glad to answer any questions which might come up. But thank you all for your time. Thank you, Ruching and Tom, for having me.